Alright, just so you know, this is the last video. So this is the last one you will have to watch in order to prepare for the test. Alright, so in this video we're going to go over some basic reactions and also some stoichiometry. So first of all, whenever we have a chemical change or a chemical reaction, it has to involve breaking bonds between the atoms of a molecule and forming new bonds to make new compounds. So you have to be creating something new. A physical change will involve breaking or making intermolecular forces between molecules. So a physical change would be something like melting, boiling. Now, when you're looking for a chemical reaction, you could see the formation of a solid, a gas, or a light, or even like a liquid like the formation of water. A change in temperature, but you have to be careful because a change in temperature does not always indicate chemical reaction. So a common misconception is that boiling water makes oxygen, gas, and hydrogen, and that's not what happens. Boiling water will just separate the molecules out. So it's still water at the end. You've just separated and moved the molecules further apart. So good way to ask about this would be to maybe have a particle diagram and asking about what happens if you boil salt water or something like that. If you're boiling water, you should not be creating hydrogen and oxygen, and you should see the molecules moving out into the gaseous phase. Alright, so some basic types of reactions would be a synthesis reaction. So if I take two compounds and make one, so if I take water and I add it to carbon dioxide, well, I make carbonic acid. And carbonic acid actually easily decomposes into the water and the carbon dioxide. But basically, if it's synthesis, I'm making one product at the end, or one type of product. Decomposition would be if I have one reactant and it decomposes into several components. So if it's decomposition, I should just have one reactant. If it's synthesis, I should have one product. A single displacement or single replacement would be if I take a piece of metal or if I take an element and then I basically switch it with another element in a compound. So a good example of this would be adding potassium to water. I'm going to create potassium hydroxide and displace that hydrogen gas. So the A will switch places with the B, and then I'll have something by itself as a product and something by itself as a reactant. Now, double displacement would be a precipitation reaction, or it could also be a neutralization reaction. So basically, you have two ionic compounds, and usually when this happens, it happens in solutions. So you take two solutions, put them together, and then the ions will swap places. So the A will switch places with the D, and you'll create a new product at the end. So with a double displacement, you should have two ionic compounds being added together. A combustion reaction is when you burn something in oxygen gas. So usually what you'll see is you have a hydrocarbon, something with carbon and hydrogen, combusting an oxygen gas. And something you really need to know, if you have a combustion reaction where I'm combusting a hydrocarbon and oxygen, I'm going to make CO2 and water, because they might ask you to write out equations like that. Alright, so, oops. An acid-base reaction would be a neutralization reaction, where you're going to react the acid, or the H+, with a hydroxide to produce water and some ionic compound. So this is my net ionic reaction, though, if I have a strong acid with a strong base. An oxidation reduction would be when you are transferring the electrons. So you'll see that in single replacement reactions too, where there's a transfer of electrons. So remember, oxidation is gain of electrons, reduction is, oxidation is loss, reduction is gain. So oil rig. Oxidation is loss, reduction is the gain of electrons. All right, so a precipitation reaction it's a double replacement reaction, but you are making a solid at the end, so that you're making a precipitate. And we use precipitation reactions a lot when we are trying to maybe determine the purity of a substance, or we're trying to isolate an ion from a mixture or another compound.
Tyler D. Gregorio, please come to the front office. Tyler D. Gregorio, please come to the front office.
So in a precipitation reaction, you're going to put two solutions together, and then you're going to make a solid compound. And usually that solid compound will be filtered out, dried, and then weighed. All right, so you might be asked to write out a net ionic reaction. So if I have a double replacement reaction, what I would do is I would write out the full reaction and balance it. So let's do this one. Let's do silver nitrate plus potassium chloride. So silver, remember silver is a positive 1 when it combines with nitrate, so it's a 1-to-1 ratio, plus potassium chloride. So we're going to switch places. So the silver will now bond with the chlorine, +1 and a -1. Check your charges, please. And then we're going to have potassium bond with nitrate. So check your charges. K is +1, NO3 is -1, so 1-to-1 ratio. All right, so now we need to decide if we're making a precipitate. So you need to know this rule. Okay, this is the only thing that College Board expects you to know at this point. If you have nitrate, so anything combined with nitrate is soluble. Anything combined with group 1 is soluble. So if it's potassium something, sodium something, those compounds will be soluble. Halides, so basically most of the time halogens are going to be soluble compounds, but that's not always the case, and that's actually not one of the rules you need to know. You need to know about nitrates, you need to know about group 1, and you also need to know ammonium salts are soluble. So anything with NH4 will also be soluble. All right, so usually in the test they will tell you maybe what the precipitate is. So the precipitate here in this case will be silver chloride. So everything else should be soluble. I know that anything with nitrate is soluble, so that's going to be aqueous. I know anything with group 1 is soluble, so that should be aqueous. And then I know potassium or nitrate, both of those things make soluble compounds, so that will also be aqueous. So the only thing that's solid is my silver chloride ion. Well, what I can do, I can break up everything that is aqueous. So silver nitrate, when I dissolve a compound into water, a soluble compound, it's going to break apart into its ions. So silver and nitrate will break up, because that's what happens if an ionic compound is being dissolved into water. It's breaking apart into its ions. So silver is a +1. Nitrate is a -1, and there's only one of those. All right, potassium, there's only one of those, and it has a charge, so make sure you're including the charges with this. Chloride is also, well, it's -1, and there's also one of it. All right, so now let's go to my product side.
Attention students, I need Joey Sahi to go to portable P6. I need Joey Sahi to go to P6 at this time.
All right, so now let's go to our product side. Silver chloride is a solid, so that means that it's not going to be broken up. And then potassium nitrate is aqueous, so I'm going to break that up. So potassium ions and nitrate ions. And let me put aqueous. All right, so now what I do, I'm going to cancel ions that appear on both sides. So nitrate is here and here, so I can get rid of it. And this is here and here. These are called spectator ions. So spectator ions do not actually participate in the reaction. They're like spectators, so we can get rid of them, and usually we prefer to have a net ionic reaction because that's what we're actually interested in, not the spectator ions. The spectator ions have nothing to do with the reaction. So now I'm just going to write it out. Ag plus 1 produces this. Ag solid. Okay, so if we're writing out the net ionic reaction, we do not include spectator ions. We need to include charges, and we also need to include states of matter. Make sure you do that. This is an easy point to get. All right, let's look at another type of net ionic reaction. Let's look at a single replacement reaction, which is also going to be a redox reaction. So let's write the full reaction here. Magnesium is added to a solution of silver nitrate. All right, so it's a single replacement reaction. I know this reaction will happen. Silver is very non-reactive. Magnesium is very reactive. So when it's a metal, it's going to be very reactive, and the reaction does happen. So the magnesium will switch places with the silver. So now we're going to have something that's by itself. So the silver will be out by itself now, and then magnesium will bond to the nitrate. So we're going to have Mg. Mg has a positive 2 charge, and nitrate has a negative 1 charge. This is why you need to check your charges, because we actually have MgNO3 too, which means I have that, NO3, and that. Okay. All right, so now that I have my full reaction, well, if I do the same process, I just take everything that's aqueous and split it, it's basically the same thing that we've been doing. So let's do that. Magnesium's a solid. It's just a metal by itself, so we're going to leave that there. This will be aqueous. Anything with nitrate is aqueous. So I'm going to pull this apart. So I have silver ions, and there's 2 of those, plus my nitrate ions, and there's 2 of those. This is aqueous, aqueous. All right, so now let's go to our product side. We'll have 2 solid silvers, and I also will break this apart because it's aqueous. So magnesium has a +2 charge, and nitrate, there's 2 of those. Has a -1 charge. All right, so let's see what's not participating. Well, this appears on both sides, so I can get rid of that. But everything else is something different. This is a solid, this is an ion, this is an ion, this is a solid. So this is what my reaction actually is. This is the only thing that's actually reacting. The silver and the magnesium, the nitrate's not participating here. Okay, so this would be my net ionic reaction. So this is my net ionic reaction. Now, because this is also a redox reaction, I could just simply pull it apart as a redox reaction. So I would look to see what is happening to my oxidation states. This is a 0 charge here, or a 0 oxidation state. This magnesium over here is a +2. Silver right here is a 0, and then right here it's a +1. Well, the nitrates don't participate in this at all still, and I could pull it apart and just write it as half reactions and put them together. So magnesium produces Mg +2, and it's a redox reaction, so I'm going to balance the charges, put 2 electrons down, and then I know silver is a +1 on this side, and it becomes Ag with a positive, or I'm sorry, a 0 charge. Well, I got to balance it out with electrons. So 1 electron on this side. So +1 and then -1. And then I would combine them, but I would have to multiply it out by 2. So it would be 2 Ag plus 2 electrons. Don't forget your charges. Produces 2 Ag silvers. Either way, you get the same answer after you combine these two half reactions. All right, so let's practice a little stoichiometry here. So when I look at this, I have a reaction, and it says I have 15 grams of aluminum sulfide and 10 grams of water. They react. Let's identify the limiting reactant. What's the maximum amount that we can make of this? How much excess reactant is left over, and what's the percent yield here? So, first thing, let's go ahead and we're going to figure out what the limiting reactant is by figuring out the maximum amount of H2S. I know this is limiting reactant, not only because it says limiting reactant right there, but because it gives me two amounts of reactants here. So I know that I have to do two calculations and pick the smallest answer. So I'm going to have 15 grams of aluminum sulfide, which is Al2S3, and 10 grams of water. So let's go ahead and go to my product because I'm going to have to calculate this anyway. So let's go to the mass of H2S for both of them. First step, if I want to go to a different substance, I have to go through the mole. So I'm going to figure out how many moles I have of aluminum sulfide. My molar mass here is 150. Okay, so now that I'm in moles of what I have, I can go to moles of what I want. Alright, so that goes on the bottom, so I can cancel it. Moles on top of moles. Let's look at the coefficients. So it's 3:1 ratio. And yes, I could stop here, but it's asking for the mass anyway, so I'm just going to go the one extra step. Grams of H2S on the top. 1 mole is equal to 34. Well, after I do this, I'm going to get to 10.2 grams of H2S. All right, so same thing here. We got to go to moles. So moles of H2O. Now I need to go in moles of what I want. Moles on top of moles, it's a 3:6 ratio, or really just a 1:2. And now I go to grams. All right, so once I do this calculation, I'm going to get 9.44 grams. And, well, I have two answers. I pick the smallest one. This is the maximum amount of H2S that I can produce. I will not get to 10.2 because once I get to 9.44 grams, I run out of water. Water is the limiting reactant because it produces the smallest amount. All right, so now how much excess reactant is left in the container? Well, I need to figure out how much of the excess reactant I used in this reaction. So the limiting reactant should be used up, so I should use up my water, but I'm going to have some Al2S3 left over. So I need to figure out how much of the aluminum sulfide I used to begin with. So what I'm going to do, I'm going to go from my 9.44 grams of H2S and figure out how much I used of the Al2S3 to get to this amount. So I'm going to go back to my excess reactant here. So I'm going to go back to moles. Then I'm going to go to moles of aluminum sulfide. All right, moles on top of moles. I have 3 moles of this for every 1 mole of this. And now I'm going to go to grams. right, so 1 mole is equal to 150. So once I do this, I'm going to calculate out 13.88 grams that were used. So I used up this much to make this much H2S. So it's asking for how much is left over. Well, I started with 15 grams. I only used 13.88. So what I have left over is the difference, which should be 1.12 grams left over. All right, and then the last one, what is the percent yield? Okay, so the percent yield comes from two numbers. It comes from the actual yield divided by the theoretical yield. Well, it says that 8 grams of H2S are produced, so that's my actual, that's what I actually made, and I should have made 9.44 grams. So let me erase. My actual divided by my theoretical. Anytime you do a calculation, it is always theoretical. So my actual is 8. I was supposed to make 9.44. This came from the calculation. So once I do that, I'm going to divide it out and multiply it by 100. So 8 divided by 9.44 gives me 8.84. So multiply that by 100. My theoretical yield will be 84.7%. Now, there was another thing I was going to go over. I was going to go over this BCA table, but actually I think there's something a little bit more important to go over, and then that's going to be the reaction of something dissolving. So not necessarily the reaction, but writing the equation for when a substance dissolves. So the dissolution equation. This is another way to say dissolving. All right, so let's say that I have a compound and it dissolves in, let's do magnesium nitrate. So if it's just dissolving, that means it's not reacting to the water. All that I'm doing is pulling the ions apart. So I'm going to separate everything out into its ion. So magnesium, when it dissolves into water, will be pulled out and then be pulled into the solution as an ion with a +2 charge. And it's aqueous. Now I'm going to look at the nitrate. Well, nitrate has a -1 charge. And there are 2 of those. So for every 1 mole,
Coach Rado, please call the main office. Coach Rado, please call the main office.
For every 1 mole of this that dissolves, I have 2 moles of my nitrate. So when you're writing an equation for when something dissolves into water, or the dissolution equation, you're basically just pulling the ions apart. So it's not reacting. All you're doing is just pulling the ions apart. So you need to make sure you have charges, make sure you have states of matter, and make sure you have the right number. So if you have 2 nitrates here, you should have 2 nitrates on this side too. And guess what? We are done. We're finally done. Okay.